Parameters affecting the wake vortex. Aircraft weight. Wake vortex strength increases with the weight of the aircraft. This is why today the ICAO aircraft classification is based on the maximum takeoff weight. However, such an approach is a simplification as other parameters also affect the strength at the separation distance. Wing characteristics. The wing shape and the load distribution affect the wake vortex characteristics, mainly through the decay rate. A smaller wingspan increases the decay rate. Therefore, for a given vortex generator or leader aircraft weight and at the same distance, vortex encounters are less severe behind an aircraft having a smaller wingspan. It has also been demonstrated that aircraft having a high inboard loading, higher deflection of the flaps close to the fuselage as an example, have a faster decay of their vortices. Weather conditions. The weather conditions play a major role in wake vortex development and decay. In the case of heavy turbulence, a vortex will dissipate very quickly and there is no risk for the follower aircraft. Strong winds are associated with turbulence and will also contribute to a rapid dissipation. Calm weather creates the most critical situation as the strength decreases slowly and the vortex effect may be felt far behind the vortex generating aircraft. Today, in order to be safe, all separations assume that the aircraft are flying in perfectly calm conditions.
Although all airplanes create wingtip vortices, the larger the airplane, the larger the vortex, and therefore, the larger effect it will have on your airplane. Wingtip vortices are the strongest when the airplane is heavy, clean, and slow. This means the airplane is close to its maximum gross weight, is not using high lift devices like flaps, and is traveling at a slow speed. The reason this particular combination creates the strongest vortices is because the airplane is required to fly at a high angle of attack to generate enough lift to keep it flying. The more the airplane weighs, the more lift is required, and if the airplane is flying at a slow airspeed, the only way enough lift can be created is by having the wings at a high angle of attack. Usually, this is most prevalent during takeoff and landing because the airplane is slow. For the most part, you should only be concerned about the wake turbulence created by larger aircraft. This does not mean that you can't encounter another smaller aircraft's wake. It is just less likely to significantly affect your airplane.
Encountering a wake vortex definitions. When an aircraft enters in the vortex of another aircraft, the maneuver is called an encounter. The aircraft emitting the vortex is called the generator and the one experiencing it, the follower. How likely is an encounter? It is not possible to implement navigation procedures such that the probability of an encounter is 0. To give an example, during the Airbus wake vortex flight tests, in cruise, Airbus 319 vortices were identified at a range of 40 nautical miles, thanks to the contrails. An encounter with such a vortex is obviously very weak, but it exists and it would have been a bit stronger behind a heavy. It is also common to have, in the initial approach phase, encounters at distances well above the ICAO minimum separations. The ICAO separations have not been set to avoid all encounters but to prevent unsafe encounters. Avoiding all encounters would require very significant separations and dramatically limit the traffic on all airports and airways without significantly improving safety. It is also to be noted that statistics show that the probability of injury to passengers and crew is about 5 times greater in turbulence due to weather than with a wake vortex encounter. Operational procedures. General procedure increases considering the way the vortex is acting on the aircraft as explained previously. If the pilot reacts at the first roll motion, to the right in the example given, he will correct by rolling to the left. When in the core of the vortex, the main roll motion to the left will then be amplified by this initial piloting action. The result will be a final bank angle greater than if the pilot would not have moved the controls. This has also been demonstrated during the Airbus flight tests. Most of the encounters have been performed stick-free, but several hundred were carried out with the pilot trying to minimize the bank angle. The results clearly show that pilot action does not improve the situation. In addition, in-flight incidents have demonstrated that the pilot inputs may exacerbate the unusual attitude situation with rapid roll control reversals carried out in an out-of-phase manner. In the case of a severe encounter, the autopilot may disconnect automatically. But in all other cases, it will be able to counter properly the roll and pitch motions generated by the vortex. For these reasons, the best procedure in case of encounter is, release the controls. Do not voluntarily disconnect the autopilot if the autopilot is disconnected. Before any reaction, wait for a reasonable stabilization of the aircraft, then, roll wings level. Re-establish the initial cruise level or the standard climb or descent trajectory. Use of rudder warning. A large deflection of the rudder creates a very important lateral acceleration that may well surprise the pilot. It could lead to a reaction with a deflection to the other side. This could then give rise to very large forces on the fin that may exceed the structural resistance. An accident has already occurred for this reason. Some recent aircraft types are protected thanks to their fly-by-wire systems, but anyway, any use of the rudder does not reduce the severity of the encounter, nor does it improve the ease of recovery. Therefore, do not use the rudder.
An aircraft's vertical stabilizer, which includes the rudder, provides lateral stability during flight. Take it away, and the airplane will wallow from side to side, lose altitude, and crash. Flight 587 was on an Airbus A300-600 aircraft. The vertical stabilizer had a unique quality. It was manufactured from composite material, layers of carbon fiber that provide a lightweight alternative to aluminum.
And we saw the 6 lugs made up of composite material broken.
Ruled out wake turbulence in the vertical stabilizer's composite material. The investigation shifted again. NTSB officials conducted interviews to determine the competency of the co-pilot, who was commanding the aircraft when it crashed.
This one gentleman was a captain in a Boeing 727 when the accident first officer was his first officer. They ran into a bit of wake turbulence, and the first officer reacted strangely. In a sense, he activated the rudders back and forth several times, causing the aircraft to yaw quite heavily.
Fully deflecting the rudder back and forth as the co-pilot had done stood out as a red flag to investigators. An analysis of Flight 587's data recorder showed that the co-pilot had once again repeated this abnormal maneuver.
He jumped the gun on responding, and that as the airplane swung one way, he came in with opposite rudder, and that the airplane then swung back and overshot in the other direction because he had put in too much rudder control. And so he then went to the other rudder pedal and tried to correct this.
This led to a shocking revelation, dispelling any theory of a terrorist plot, that a pilot could inadvertently cause severe structural damage to an airplane at maneuvering speed.
Maneuvering speed is a speed below which, in the general understanding of pilots, any deflection of the controls can be made with any speed, any violence. The plane can be maneuvered in any way you choose without endangering the structure. However, it turns out that there was some fine print in the certification of airplanes, and one of the provisions in the fine print was essentially that you couldn't flap the rudder back and forth the way this pilot allegedly had done.
The A300-600 was somewhat susceptible to this type of anomaly. At the speed the aircraft was traveling, about 250 knots, it only took about 1 1/4 inches of rudder travel to move the rudder all the way to 9.3 degrees either way, and it only took about 32 pounds of rudder pedal force. And it takes 20 pounds just to get the rudder to move, so there's not a lot of margin there at all.